Okay, so here is something a bit unexpected. Imagine you have a pressure gauge and you slowly bring it up to 60 psi. It reads 60.2. Fine, close enough. But now you start at 100 psi and you bring it down to 60 psi. Now it reads 59.8. Same input, different output, depending on which direction you came from. That's hysteresis. And in instrumentation, it matters more than people think. The formal definition is straightforward. Hysteresis is the difference in an instrument's output for the same input value, depending on whether that input was approached from the increasing direction or the decreasing direction. Look at the graph on the slide. You have got two curves, one going up, one coming down. In a perfect instrument, they would sit right on top of each other, both following that ideal straight line. But in the real world, they don't. They separate. And that gap between them, that's your hysteresis. Let's make this concrete. As a first example, say you have got a pressure transmitter calibrated from 0 to 100 psi. When pressure rises from 0 up to 60 psi, the output reads 60.2. When pressure drops from 100 back down to 60 psi, the output reads 59.8. That's a 0.4 psi difference. And that's the hysteresis error. It doesn't sound like much, but in a tight control loop or a safety application, that kind of consistency can cause real problems. The takeaway here is simple. The path matters. Not just where you ended up, but how you got there. So, why does this happen? It's not random. There are very specific physical reasons why instruments behave differently on the way up versus the way down. Let's look at those. The most common culprit is mechanical friction. In gears, linkages, pivots, anything that moves and rubs against something else has friction. And a friction means the element doesn't return to exactly where it was. Then you have got elastic deformation. Think about Bourdon tube or diaphragm. These are the sensing elements inside a lot of pressure in instruments. When you apply pressure, they deform slightly. When you remove that pressure, they mostly spring back, but not always perfectly. That tiny residual deformation shows up as hysteresis. There is also something called magnetic remanence, relevant in instruments that rely on magnetic materials. Some magnetism lingers after the field is removed, which bias the reading. And finally, mechanical backlash. That's the play you feel in a gear, joint, or mechanical linkage. When direction changes, there is a small dead zone before the mechanism actually engages. That creates a lag, and that lag is hysteresis. Well, now, what do we do about it? First, material choice and build quality matter a lot. Using high quality materials with tight tolerance reduces mechanical play significantly. If your components fit precisely, there is less room for that dead zone effect. Lubrication. Lubrication is another straightforward one. Reducing friction between moving parts helps the mechanism return more consistently. But honestly, the most effective approach in modern instrumentation is to move away from purely mechanical sensing elements altogether. Electronic Electronic sensors like strain gauges, capacitive sensors, piezoelectric elements. These have dramatically lower hysteresis than mechanical designs. There is simply less physical slope in how they work. And if you are in a situation where hysteresis can't be designed out, maybe you are stuck with an older mechanical instrument, the practical answer is to calibrate in both directions, upscale and downscale. You document both responses and you account for the spread in your uncertainty budget. So, to recap, hysteresis tells you that an instrument history matters. The reading you get depends not just on the current input, but on whether you arrived there from above or below. The causes are mostly physical: friction, deformation, magnetism, backlash, and the fix is either better components, electronic sensing, or, when all else fails, calibrating in both directions. Keep this in mind, especially when you are working with older mechanical instruments or any application where the process variable cycles up and down frequently. Thank you. See you next lesson.